Now that we know the three postulates of Bohr's model, let's try and find the radius and the energy equations using the Bohr's postulates. So based on the second postulate of Bohr, we know that the angular momentum of an electron will be an integral multiple of the value h by 2 pi. We also know from our knowledge of circular motion of objects that angular momentum is given by the mass multiplied by the velocity multiplied by the radius of the orbit of the object around the central point. So when we equate L is equal to m into v into Rn with L is equal to nh by 2 pi, which is as per Bohr's second postulate, we get equation 1, that is mvn Rn, where Vn stands for the velocity of the nth orbit and Rn stands for the radius of the nth orbit. M is the mass of the electron, and on the right side you have nh by 2 pi. So let's name this as equation 1. So using this, we will carry forward from our previous equations. We know that radius of a Rutherford model for an electron is given by r equal to e square by 4 pi epsilon naught mv square. We can also rewrite this by taking v, or velocity, on one side and taking all the remaining terms to one side. So we can rewrite this equation as velocity of nth orbit is equal to e by square root of 4 pi epsilon naught m into Rn. So we'll call this equations 2 and 3. Now we can combine 1 and 2 to find out the value of r. We can also combine 1 and 3 to find out the value of velocity. So let's combine 1 and 2. We get mvn into e square by 4 pi epsilon naught mvn square equals nh by 2 pi. So what I've done is, on the left hand side, instead of Rn, I have put the value from equation 2 into equation 1. So I strongly suggest you take a sheet of paper and pause the video at this moment and then write down each of these steps so that you understand this better instead of just having to look at the video. So I strongly recommend that you do this along with me so it becomes easier. So from that step, we reduce by cancelling out like terms on both sides of the equation, and we are left with e square equals e square by 2 epsilon naught Vn equals n into h. So keeping Vn on one side, we arrive at the final form. Velocity in the nth orbit is given by e square by 2 epsilon naught nh. So this gives us the velocity in terms of the fairly known quantities, all of which are fixed. Epsilon naught is fixed, nth orbit, h is Planck's constant, e is the charge on an electron. Similarly, when I combine 1 and 3, I'll get the value of Rn. So again, now this time what I'm doing, in equation 1, I'm replacing Vn with the value of Vn from equation 3. So I get m into Rn into e by 4 square root of 4 pi epsilon naught mRn equals nh by 2 pi. So let's square on both sides to remove the square root. We get the above form, m square r square e square by 4 pi epsilon naught mRn equals n square h square by 4 pi square. Again we cancel out like terms, and eventually, keeping Rn on one side, we arrive at the final form, Rn equals n square h square epsilon naught by pi me square. So we'll call this equation A. Now for a hydrogen atom, we know that n is equal to 1. So I can calculate the value of the radius of the very first orbit. So Rn will be equal to R1, which is equal to h square epsilon naught by pi me square, because n square has disappeared because I put, instead of n, I put 1 there. So it is, equation A has reduced to this form. This equation is called the Bohr's radius. When n is equal to 1, the value of Rn or R1 is called the Bohr's radius, and it's denoted by a special letter A naught. So A naught equals h square epsilon naught by pi me square. Now we know all the values of the terms on the right hand side. So if I substitute all the values on the right hand side, I get the value of A naught to be 5.29 into 10 power minus 11 meters. Again, I strongly suggest you do this calculation yourself on a piece of paper using a calculator and see if you are getting this value. So this is about 0.529 angstroms. Similarly, from A we can also deduce one more thing, that the radius of the nth orbit is proportional to the square of the value of n, which means Rn is proportional to n square. Radius of an orbit increases by a factor of n square as we go to higher orbits. An important point, so please note it down at a place where you can get it back for quick reference. Now, having known the radius, we can also calculate the equation for energy. Again, if you go back to some of our previous equations that we derived in the class, you'll know that the energy of the nth orbit is given by minus e square by 8 pi epsilon naught Rn. So please refer back to your class notes and you'll know that we had done this derivation on the board. Now again, I substitute the value of Rn from equation A into this. What I get is En equal to minus e square by 8 pi epsilon naught n square h square epsilon naught by pi me square. Simplifying this, I arrive at equation B. En equals minus me to the power 4 by 8 n square h square epsilon naught square. With the exception of n square, I put all the other values that I already know, and this equation B reduces to En equals minus 2.18 into 10 power minus 18 by n square joules. If I convert this into electron volts by dividing it by the value of 1.6 into 10 power minus 19 coulombs per charge, then I get this reduced to En equals minus 13.6 by n square electron volts. So again, here you can observe that energies of orbit decreases by a factor of 1 by n square as we progress into the outer orbits, whereas radius increases by a factor of n square as we progress into outer orbits. Two very key points that is worth remembering. The Bohr model, though it successfully explains some of the shortcomings of the Rutherford model, unfortunately has its own limitations. When Niels Bohr tried to explain the shortcomings of the Rutherford model, he used the simplest atom for the purpose, and that was a hydrogen atom that comprised of a single electron going around the central nucleus. So the Bohr model's postulates work well for hydrogen or hydrogenic atoms or ions, which means atoms or ions that are similar in structure to the hydrogen atom, that is having only one orbit with a single electron revolving around the central nucleus. The second limitation is that it fails to explain the variation in frequency intensities in an emission spectrum. If you remember, when I showed you the emission spectrum in the previous slides, you could see that the lines, one aspect was that the lines were unevenly spaced. The second aspect was the lines towards the left had dimmer and dimmer in terms of intensity. So this dimness in terms of intensity was something that the Bohr model failed to explain. Third, it fails to explain the Zeeman effect, that is the splitting of the spectral lines under the influence of magnetic field. Though we haven't spent some time on this concept, this is yet another drawback of the Bohr's model. It could also not explain the ability of atoms to form molecules through chemical bonds. We know chemical bonds are interactions between electrons of two different atoms to form a molecule. Now, when this used to happen, the Bohr model used to fail to explain how this could happen. So the major reason that we know today why the Bohr model failed is that since it considered a hydrogen atom for its purpose, Niels Bohr did not take into account that electrons in the lower orbit may also be influenced by electrons in the higher orbits. Whereas when he took a hydrogen atom for the purpose, the atom's single electron was only being influenced by the nucleus and not by any other electron. Whereas if you go to the very next element, that's helium, there are two electrons, and not only do these individual electrons get influenced by the nucleus, but even the electrons have an influence on each other. So it is that electron-electron influence that Niels Bohr failed to take into account in his three postulates. So these are some limitations of the Bohr model. Next we move on to energy levels. So based on the energy equation that we derived using the Bohr model postulates, we could also construct an energy level diagram. So each level in this diagram corresponds to an orbit around the nucleus. So you can see the diagram on the right. You can see at the bottommost line is what is called the ground state. This is when n value is equal to 1. So you would have realized by now that this energy level or the ground state refers to an electron orbiting the nucleus at its innermost orbit. The next orbit, where n is equal to 2, is quite a distance away from the center, from the lowermost orbit. Then when n equal to 3, it goes a little further away, and so on, until at some point the lines are so close that we say that if some electron is at this level, it's almost unbound to the atom, or the atom is said to be ionized. So the energy of an atom is the least when its electron is revolving in an orbit closest to the nucleus. So the energy of an atom is the least when its electron is revolving at an energy level closest to the nucleus. Which means, if you remember the previous equation, we said energy level at the nth orbit is minus 13.6 electron volts divided by n square. Right? So the energy level is the least when the electron is orbiting at the closest orbit to the nucleus. Remember, we are only speaking of a hydrogen-like atom which consists of a single electron. Now the lowest state of an atom is called the ground state. This I have already mentioned, and at the ground state we denote the radius by a special symbol called A0, or the Bohr radius. And to free an electron from this particular orbit of a hydrogen atom, the amount of energy that has to be supplied is the highest, and that is 13.6 electron volts. That is called the ionization energy of the hydrogen atom, because once the electron is successfully freed from the atom, what's left is only the nucleus, and that nucleus is termed as a hydrogen ion because it requires a positive charge because of the proton in there, but the electron is missing. So this is about energy levels. So we'll study this a little more. So at room temperature, most of the hydrogen atoms are in ground state. So when you have ordinary hydrogen at room temperature and pressure, most of the hydrogen atoms are in ground state, which means that single electron in a hydrogen atom is revolving around its nucleus at the innermost orbit n equals 1. Now when a hydrogen atom receives energy by processes such as electron collisions, or in the initial experiment that we did wherein we said low pressure hydrogen gas was taken in a tube, remember that pink tube, and it was excited by electric current. Then energies are absorbed by the electron and the electron jumps to a higher orbit. If it receives a total of 13.6 electron volts, it completely becomes free from the atom, but it may not receive that much of energy. So it may just receive enough energy for the electron to jump from n equals 1 to possibly n equals 3, or possibly n equals 5, or possibly n equals 2, depending on how much of energy has to be supplied. The difference has to be supplied by the external source. Now when an electron has jumped from in a hydrogen atom from n equals 1 to any of these orbits, we say the atom is now in an excited state. The atom is said to be in an excited state. It's not in the ground state, but it's in an excited state. Now from these excited states, the electron will now, after a few passage of a few moments of time, the electron may fall back to the ground state again. So if something falls back from the second orbit to the ground orbit, if an electron falls back from the second orbit to the ground orbit, then it will release a photon in the process, and that photon will have an energy that is the difference between the initial state where it was here and the final state where it's here. So minus 3.40 minus of minus 13.6 electron volts. So that is the energy of the photon that will be liberated. Similarly, if an electron jumps from n equals 4 to n equals 1, then the photon that's released will have an energy that's equal to the difference between minus 0.85 and minus 13.6. Thus, as the excitation of hydrogen atom increases, that is, as n increases, the value of minimum energy required to free the electron from the excited atom decreases. That's very obvious, because if you have already excited the hydrogen atom and the electron has already jumped from the ground state to one of these states, the extra energy that's required to completely free the electron from the atom's nucleus is much less as compared to when the same electron is at the ground state. So that's why this statement, as the excitation of hydrogen atom increases, the value of minimum energy required to free the electron from the excited atom decreases. The third postulate of Bohr, if you recall, states that whenever an electron falls from an excited state, what we call as the initial state, to a lower orbit, or possibly to the ground state, which we call as the final state, then the postulate says that a photon is released with an energy that is equal to the difference of the energy levels between the initial state and the final state. So as shown in the screen, you can see h nu of the electron or the photon is equal to the difference in the energy levels from the initial state to the final state. So over here, if I substitute both E subscript Ni and E subscript Nf with the energy equations that we derived from the Bohr's postulates in the previous screens, we get the photon energy h into nu of the initial state as m into e to the power 4 divided by 8 epsilon naught square h square into 1 by the integral number of the final state minus the integral number of the initial state. Now when I take h to the right hand side, what I'm left with on the left hand side is the value of the frequency. Now frequency, you might know, is the reciprocal of wavelength. So 1 by lambda, or on the left hand side, is equal to the equation that you see, the terms that you see on the right hand side. Now you might have recognized that this term over here, m e to the power 4 by 8 epsilon naught square h cube, is nothing but what we used to mention as the Rydberg constant when we are talking of the Lyman series, the Balmer series and other series, spectral series of lines previously. And if you replace this term, all these terms, with the letter R for Rydberg constant, you get the empirical value or the empirical formula that was arrived upon by Balmer. So this is where you can now see that Bohr's third postulate could satisfactorily explain what Balmer and the other scientists who had discovered the spectral lines had seen on the atomic spectra. Right? And both these formulae, which were derived empirically and through Bohr's third postulate, they match very well. About 10 years after Bohr's postulates were put forth, there was still the question of why the angular momentum of an electron should be an integral multiple of nh by 2 pi. So what is it with the value nh by 2 pi that an electron is forced to take either this value h by 2 pi or some integral multiple of the value h by 2 pi. So why should it be quantized? Why can't it take any random value? This was the question which was being worked upon by several scientists, and de Broglie put forth an explanation as to why this has to happen. De Broglie made use of the wave theory to explain this particular finding of the Bohr's second postulate. What he stated was that when a string or a rope is plucked, several different wavelengths are produced, but most of the wavelengths, they cancel out each other very quickly. The only waves that remain are called the standing waves, and these standing waves are formed when their nodes are at either ends of the plucked string, which means another way of mathematically explaining it is that the length traveled by these waves from one end to the other end and back should be equal to the wavelength of that particular wave, or it should be an integral multiple of that wave. Only then such waves contribute to the formation of standing waves, which means when applying this concept, de Broglie took the left hand side to be equal to 2 pi. So it should be 2 pi or an integral 2 pi, or which is the wavelength of one full circle, multiplied by the radius, which should be equal to n times the wavelength. So 2 pi Rn should be equal to n times the wavelength of the electron. So substituting lambda with substituting the right hand side lambda with h by mvn, we get 2 pi Rn equals nh by mvn. So taking m to one side and vn also to the left hand side and bringing the 2 pi to the right hand side, we get mvrn equals nh by 2 pi, which is exactly what was stated in Bohr's second postulate. Laser stands for light amplification by stimulated emission of radiation. So usually light is emitted from any source in the form of packets of waves. So ordinary light actually is a mixture of many wavelengths, and there's no phase relationship between the various waves. Thus these waves spread out fast and the beam size rapidly increases with distance, dimming out the intensity. But in the case of laser light, the wavelength of each packet is almost the same, and the average length of the packet of waves is much larger. This means the phase correlation is better over a longer or lengthier duration of time. This results in reduction in the divergence of the beam and hence the retention of the intensity. Now if there are n atoms in a source, each emitting light with intensity I, then the total intensity produced by an ordinary source is proportional to n atoms multiplied by the intensity. But in the laser source, if there are n atoms in a source, each emitting light with intensity I, then the total intensity produced is proportional to n square multiplied by the intensity. Thus, due to the fact that n is the number of atoms in a source and n is typically very large, the light from a laser can be much stronger than an ordinary source.